Now we are going to discuss the second operation on a binary search tree, which is insertion or creation of a binary search tree. So let us take the example. We have values given 43, 10, 79, 90, 12, 54, 11, 9 and 50. We have to create a binary search tree using the following data. So in a binary search tree, one thing we know, once we have a particular node, every other node which we insert on its left subtree should be less than the particular node, and every node which is inserted as the right subtree should be having values greater than that node. This is the condition. For every node, this condition is the same. Take the first value, it is 43. So let us make the node with value 43 and insert it as the root node to the tree. 43 is now the root node. Step 1, we have made 43 as the root node and we move on to the next value. Next value is 10. So 10, is it lesser or greater than 43? It is lesser. So where should it go? It should go to the left subtree. So I added the value 10. That node is added as the left child of root node. Why? Because it is smaller than 43. Move to the next value. It is 79. 79. Now after step 2, I have 79 to insert. Where should it go now? 43. Start from the root node. Compare the value, new value. New value is greater than the root node. So where should it go? It should go to the right subtree of 43. So we have added 79 as the right child of root node. Then what is the next value? It is 90. So at this step we have 43, 10 as its left child, 79 as its right child. So we have to enter 90 now. Start from the root node 43. 90 is greater. So move to the right. We are at 79. Yes, 90 is again greater. So we have to insert 90 after 79 as the right child. Why? Because 90 is greater than 79. So it must go to the right subtree of the 79. We have added 90 as the right child of 79. Now, which is the next node to be inserted? It is 90. Yes, we have inserted 90. We have inserted 90 as the left child. Then next node to be inserted is 12. So at this step, at step 4, 12 is incoming. Where should we enter that? Start from the root node 43. 12 is lesser than 43, so we know that 12 should move to the left subtree. Then I am at node 10. 12 is greater than 10, so it should be added here as the right child of 10. Why? Because 12 is greater than 10. So we added 12 as the right child of 10. What is the next value? It is 54. Okay. Start scanning from the root node. 54 is to be added. 54 is greater than 43. So move to the right. 54 is lesser than 79. So we have to add 54 here as the left child of 79. Yes, we have done that. So 54 is added as the left child of 79. At this stage, we have 11. Where should we add 11? So start from the root node 43. 11 is less than 43. So move to the left child. We are at 10. 11 is greater than 10. So we move to the right child of 10. There we are at 12. Compare 11 with 12. So 11 is less than 12. So we have to add 11 at the left subtree of 12. So we attached 11 as the left child of 12. It is now at the correct location. Then 9 is incoming. Then what should we do? 9 is coming. At this stage, we have to add a new node 9. Where do we insert it? Start scanning from the root. Okay. We are at 43. 9 is less than 43. Move to its left child. 9 is less than 10. So, we have to add it as the left child of 10. See, here we have added 9 as the left child of 10. Next, we have to add 50. So, start from the root node. This is the root node. 50 is greater than 43. So, we have to move to the right. 50 is less than 79. So, we have to move to the left. 50 is less than 54. So, we have to move to the left and add 50 as the left child of 54. So, we have added 50 here. So, that is about inserting a new node into a binary search tree. Let's see the pseudocode. Tree node insert element. There the arguments are root node and the element to be inserted. If root equal to null, that means the node to be inserted is the first node of the tree. So add the newly created node as the root. So root points to the newly created node. Otherwise, if value of root is less than the item, means that we have to traverse towards the right, because new item is greater than root. Then new item should be added somewhere at the right side of the root node. Otherwise, we have to traverse to the left, because it is a case when new value is lesser than root node. Then we have to add the new value somewhere at the left subtree of the root node. Then complexity analysis of this algorithm. Since the new node is inserted at the leaf, the highest value possible for this is the height of the tree, and therefore like the worst case complexity of insertion, the worst case complexity of this algorithm is big O of n. So if you see at look at this example, every time we are entering the new node as a leaf node, then the worst case complexity will be equal to big O of n. Now we will discuss the deletion operation from a binary search tree. We have a binary search tree and we are asked to delete a particular node from the tree. After deletion, the tree should be again a binary search tree. The condition should be of that of a binary search tree. That is the requirement. So, when we talk about a node, just visualize a node. It can have different situations. A node can be a leaf node, or it can have 0 children. A node with 0 children is possible. Then a node with 1 child is possible, either a left child or a right child. Such a node is possible, isn't it? The third case is a node may have a left child as well as a right child. That is, the node can have 2 children. By children, we can say that a left subtree and a right subtree. So that is the 3 possible cases. We are trying to delete a particular node from a binary search tree. And in front of us, there is three different scenarios. One is node has no children at all. Other one is node has one child. Third one is a node has two children. So here it is case 2. This is case 3. Okay. So what if the node has no children? What if the node has no children? Suppose in this tree we are trying to delete 44. We are deleting 44. The node 44 has no children. It is a leaf node. So traverse till node 44. Then what is to be done? Just delete that node. That is enough. Deleting that node makes no change to the condition of a binary search tree, isn't it? So if we delete this node and free up that space, there is no change for condition of a binary search tree. The remaining thing is the binary search tree again. So we have to, if you are using linked list, we have to make the link field of 33 to null. So it points to nothing. That is the right link field of that right child field of 33 to null. So it has no right child anymore. That is the only operation. Then free up this node using the free function. So this is the tree after deletion. Again, this tree is a binary search tree, satisfying all the conditions of a binary search tree. So if a node to be deleted doesn't have any children, just delete that node right away. That is easy case. Then node has one child. Suppose that we are deleting the node 75. If the node has one child, what we have to do is we have to delete 75 now. So after deleting 75, this 66 is now having no parent, isn't it? So after deleting 75, attach 66 to its grandparent. Who is its grandparent? Its grandparent is 60. Parent of 66 is 75. Its parent is 60. That is the grandparent of 66. So if there is only one child, attach that child to the grandparent. That is the step. So attach 66 to the grandparent, that is 60. This is the method of deleting a node with just one child. Now the third case. If the node to be deleted has two children, what is to be done? There are two methods. First method is we can replace that victim node with the in-order successor. Method 2 is that we can replace the node with the in-order predecessor. So let us consider the example. This is the original tree where we are going to delete a node. Suppose we are deleting the node, deleting a node with two children. Suppose we are deleting 25. If we are deleting 25, the in-order successor of 25 is 33. 25 in-order successor is 33. Then we have to move 33 to the position of 25. So here we will write 33. Now 33 is going from here, and if you look at this node, it has now no parent because its parent is being moved to some other location. Now we have to connect this child node to its grandparent. So we will connect 44 to 50 as the left child of 50. Why? Because it is being connected to its grandparent. So this is one example. Now what is in-order successor? What is in-order successor? In the previous lectures, we have learned how to find the in-order traversal or in-order pre-order and post-order traversing of a binary tree. Similarly, perform an in-order traversal on this tree. And for a particular node, the next node in the series of in-order traversal will be the in-order successor. The previous node in the series is the in-order predecessor. So, consider node 25. Keeping it as a root node, you can find the in-order traversal for that particular subtree, starting with root node 25. Then, to find the in-order successor, there is an easy method. That is, consider its right subtree. This is the right subtree of root 25. Look which is the least value. Here the least value is 33. That is the in-order successor of node 25. Okay. How to find in-order successor easily? So without doing that entire in-order traversal, just look at the right subtree. Find which is the least value. That is the in-order successor. Now we have mentioned another term, in-order predecessor. For that, look at the left subtree. For any node, look at the left subtree. There, which is the largest value? That is the in-order predecessor. Okay, we'll see it in another example. In this case, we chose the in-order successor method. So, if you perform the in-order traversal, the successor is 33. So, replace node 25 with 33. Then, when this node is moving from here, we have to attach its child to its grandparent. That is the figure shown here. After deleting 25, this is the result. Node 33, which is the in-order successor of 25, will be written there, and the necessary changes have been made where 33 has been moved. So, you can find the in-order successor by calculating the in-order traversal. We get a series by calculating the in-order traversal. Otherwise, what is the in-order successor of node 60? To know that, in-order successor, when you hear that term successor, understand that it is somewhere towards the right. Successor means next. Right. That is the thing. So, successor will be on the right side. On the right side, lowest value. That is the in-order successor. To remember easily, our value is 60. Then what is the closest value? You can remember like that. Value closer to 60. That is least value in the right subtree. Least value in the right subtree. That is closer to 60. That is 66 in this case. The in-order successor is 66. And what is the in-order predecessor in this case? For node 60. What is the in-order predecessor? This is the left subtree. Predecessor. Thinking about that term, understand that predecessor towards the left. So it is in the left subtree. Find the value which is closer to 60. So we have to find the largest value among these. Which is the closest one? 50 is the closest one to 60. So it is the in-order predecessor. Okay. So in order traversal of a binary search tree, we will get the values sorted in ascending order. Okay. In this case, we will get the values sorted in ascending order. That is the in-order traversal of the binary tree, binary search tree. Look at another example. We have the following tree and we are going to delete the node 60. 60 is having a lot of children, isn't it? It has a left subtree, It has a right subtree. Now, how to delete 60 and what will be the resulting binary search tree after the deletion? So, let's see what happens. First, I have done an in-order traversal on this tree using the algorithm we have learned in the previous video. So, this is the result of performing the in-order traversal of this tree, and we are going to delete root node which is having value 60. So in the in-order traversal, 50 is the predecessor, 66 is the successor. In-order successor and in-order predecessor. We will see both the methods. We will see what will be the resultant tree after replacing the node with the in-order successor. What is the resultant tree after replacing it with the in-order predecessor? We will see both the cases. So I have written the in-order traversal result here. So instead of doing this traversal, you can just look at that figure and identify what is the in-order successor. Successor means towards right. Predecessor means towards left. So from a node successor, so to the right subtree, which is the closest value. That is, what is the least value in the left subtree? That is the in-order successor. The largest value in the in the left subtree, that is the in-order predecessor. Predecessor means left subtree, successor, look at the right subtree. So we have to delete 60. What is to be done? Find, so which method is this? This is, we are going to replace the node with its in-order predecessor. So we have to find what is the in-order predecessor. In this figure, what is the in-order predecessor of 60? For that, consider its left subtree and pick the largest value. What is the largest value in the left subtree? It is 50. So, we must delete 60 by replacing 60 with 50. We will replace 60 with the value 50. So, the node 50 is going towards this place, is going towards 60. So, 50 will move. Then 50 has a single child, isn't it? It has a left child, or we can say that the 50 has a left subtree. So, what is to be done? Attach that left child to its grandparent. So, we just attach 33 to its grandparent as its right child. Okay. So after moving 50 to the root node, we have to attach 50's child to its grandparent. Now it is a right subtree of 25, and this is the resultant figure. Look here. This is the result. 50 is now moved to the place of 60. Then once 50 was deleted from this location, we have to attach 50's children to its grandparent. The grandparent is 25. So that is redrawn here. Hope it is clear to you. So this is how we delete a node with two children using the in-order predecessor method. Now we will see how to delete the node using the in-order successor. So I have to delete the node 60. What is its in-order successor? I have to search in the right subtree. In the in-order traversal, which is its in-order successor? That is the lowest value in its right subtree. That is 66. It is closest to 60. So I have to replace this 60 with 66. I have to move this node to this position. Then what will be the result? I will delete 60 and I will store the node with the 66 here, and it is a leaf node, isn't it? 66 is a leaf node, so I do not need to make much changes. So let's see how the result look like. So 60 was replaced with 66 now. And since it was a leaf node, we do not need to make further changes. So 75 is the right child, and the left subtree remains the same, no changes was made there. So this is another or equivalent representation of a binary search tree after deleting a node. We deleted a node 60. This is an important topic. We will be asked to delete a particular node from a tree, binary search tree. You can use either of the two methods. Just specify which method is being used. Okay. So these are the two methods. You can use any of these. And look at this resultant tree. Is it a binary search tree? Yes, it is a binary search tree. Root is 50. Every node on its left subtree is having lesser values. Every node on its right subtree is having lesser values. If you take any node, this condition satisfies. Take the node 33. It doesn't have a left subtree, but it has a right subtree and its value is greater than 33. Look at any node, this condition will hold. So it is a binary search tree again. So the condition is that after deleting the node, it should again be a binary search tree. Okay, so we have seen two methods while the node to be deleted has two child nodes. Hope it is clear to you. There is no issue whether there is multiple children, like multiple levels in a subtree. There is no issue like that. There can be a big subtree. In this case, the root node, while we used the in-order predecessor method, the subtree had 1, 2, 3, 4 levels. Still, it was not a problem to make the changes. So if this node 50, okay. So if this node 50 had another child, it will be the largest value there. So we will have to replace it with that node. Suppose that we can take another example. Suppose that in the original tree, if 50 had a child 54 as its right child, now to delete 60, to delete 60. So 50 had a right child. Suppose that in the original tree, this is another question. Okay, this is a new question. We have a tree like this. There is 54 as the right child of 50. Then use the in-order predecessor to delete the node 60. Now what is to be done? Who is the in-order predecessor now? For this particular tree, the in-order predecessor of 60 is, yes, obviously 54. Why? Because it is the largest value in the left subtree. It is the closest value in the left subtree, closest to 60. So take the closest value. That is the thing. So we will have to replace 60 with 54. Then things are easy because 54 is a leaf node. So deleting it doesn't make any big changes. So just delete it. And this will be the resultant tree. So this was another example. So we will do further examples and just practice this question. It is a very important thing. So this is about deleting a node from a binary search tree. Let's look at the algorithm. Step 1, check if the root is null. If the tree is empty, then return that is an empty tree. Otherwise, if the value of root is less than item, recurs to the right subtree. That is, the value to be deleted is greater than the root node. Value to be deleted will be on the right subtree. So move to the right subtree and do the procedure as a recursion. For every node, the same thing is happening. So it is a recursive algorithm. Okay. If root is greater than item, which means that the item to be deleted is lesser than root node. So item to be deleted will be somewhere on the left subtree. So recurse the left subtree, perform the same steps there. If the both conditions are false, that means the root value, the node we are currently at, is the node with the deleted item. So we have to perform the deletion steps. Case 1, the node has no child, so directly delete that node. It is a leaf node, so no more complications. Just delete that and deallocate the space occupied by it using the free function. Okay. Case 2, the node has one child. If the node has a single child, replace the root by its child. That means the child of that node will be connected to its grandparent. Now case 3, the node has two children. So find the in-order successor of the root. I have mentioned just one algorithm here using the in-order successor. Where is the in-order successor located? In the right subtree. Which one? In the right subtree, the lowest value. That is the in-order successor. In the left subtree, the highest value, it is the in-order predecessor. You can choose that algorithm also, no problem. But now we have mentioned just one thing. Find the in-order successor of the root. It is the smallest element of its right subtree. Let's call it the new root. Replace root by its in-order successor. Now recurse to the right subtree and delete the new root. Return the root. This is the algorithm for deleting an element from a binary search tree. Now it's pseudocode. If root equal to null, return root. The tree is empty. Otherwise, recurse to the right subtree. If item to be deleted is less than root, recurse the procedure to the left subtree. Otherwise, if the value is equal to item, we are at the node to be deleted. Then what is to be done? If there is no child nodes, delete it and free up the space. If there is one child, either left child is null or right child is null, then delete the node and attach its child to its grandparent. Otherwise, if the if the node has two children, then what is to be done? Find the in-order successor, then replace the node with the in-order successor. Here, the in-order successor is named as new root. Okay, replace the value of root with value of its in-order successor. Then what is to be done? We have to delete the in-order successor. So that is the steps. Look at this example. Consider a tree. So suppose that we are deleting a node 60. We are deleting node 60. Now how to delete that node? Okay, let's see how to delete. We have to delete 60. We are using the in-order successor method. Who is the in-order successor? In-order successor is the closest value in the right subtree. That means in the right subtree, which is the least value, that is the closest one to the root, isn't it? So it is the in-order successor, that is 66. So our algorithm says that find the in-order successor. We have found the in-order successor. Then what is to be done? Replace the value in root with the value of in-order successor. So we have written 66 instead of 60. What is the next step? Delete in-order successor, because we have shifted the in-order successor to another position, isn't it? So we have to delete that. Now we have to call the deletion procedure again. To delete this node, it is a leaf node, just delete it. Okay, we are calling the same function recursively to delete the in-order successor. Suppose that we are using the in-order predecessor in this case, how we will proceed? Let us check that also. The in-order predecessor is the largest value in the left subtree. In this case, the largest value in the left subtree is 50. So, what we have to do? We have to replace the value 60 with 50. So, when you are doing this method, just mention that the method used is replacing by in order predecessor. If you are using the other method, just mention that we are using in order successor method. Both are correct, but two different methods. Both are having giving us the correct tree. So now we have replaced 60 with 50. Next step, we have to delete 50 from here. Again, call the same algorithm, deletion. 50 has one child or one subtree. It doesn't have a right subtree, it has a left subtree. So what we have to do? We have to attach this child and anything attached with it to its grandparent. Its parent is no more. So attach it to its grandparent. Whatever is attached to this node will remain the same. So attach 33 to 25. So the answer will be, we will have 33 attached to 25. After deleting 50, we will have 33 at this position. Then 44 is a right child of 33. So we will have 44 as the right child. So if you are using in order predecessor method, this will be the result. Okay, thank you.